Let's talk about the final value theorem. What does it say? Well, it says that in our limit as s approaches infinity for our little y of s is going to be the same thing as the limit as s approaches 0. It's a much easier number to put. As of s times capital Y of s. As long as all the poles are on the left-hand side of the complex plane. So they're all real and negative. I mean, they don't have to be real, but they have to be, the real part has to be negative. Now, this says also, of course, that if one of the poles is 0, then this doesn't work because it's not on the left-hand side. It's going to be in the middle. So, special case to remember. Now, let's give an example. So, let's say we have a little u of s, step input. I'm going to start with a very basic example. That is 0 for when t is less than 0, or we have 1 when t is greater or equal to 0. So our capital U of s is going to be equals 1 over s. Then we know that our capital Y of s is equals to capital U of s times h of s, capital H of s. But we know that it's just going to be equals to h of s over s if we replace our U of s. So that means that when we use our limit as s approaches 0, we use our theorem, we do s times capital Y of s, then we're going to have s times h, of course, the s approaches 0, so we're going to say 0. Actually, no, let's leave it as s for now, and let's keep our limit. I think it's a little clearer. Divided by s. So these two simplify, and we end up with, it's pretty much like L'Hopital rule. So we end up with h of 0. Now, of course, in this case, I wasn't given a value of, a function for h, but um, uh, that's our final value theorem worked out. So this value is also called the steady state gain or the DC gain of the system. Now let's try to do a little harder example. Let's say we are given an h, and that our h function, in terms of s, of course, capital H, is going to be equals to 2s plus 4 over s squared plus 5s plus 4. Well, I'm going to rewrite it, first of all, as 2 times s plus 2, simplifying that a little bit. And then we have, let's see, what is it? 4, 1. So we have s plus 4 and s plus 1. Now our input function u of, actually it's t, I don't know why I wrote s before, is going to be equals to 0 for t less than 0, and then we just say 5 for t greater or equals to 0. So our capital U of s is gonna be equals to 5 over s. Okay, so far enough. So we're just gonna find our capital Y of s, then it's equals to U of s, H of s, and then we have 5 over s times what we have over here. Now let's apply our theorem. So we said that limit as s approaches 0 over s y of capital Y of s is then going to be equals to, again, limit s approaches 0 of s times 5 over s times, well, this part here. Okay. Now we can simplify a couple of things. We can see that these two s disappear, so we are left with our limit. I'm just going to write it clearly, skip this amount of steps possible. 10 times s plus 2 over okay, s plus 4 times s plus 1. Now we can plug in our s to be 0, but we can say that's going to be equals to 20 over 4, or just 5. All right. So this is our steady state. We can say that our y, little s, or steady state is equals to 5. Uh, very simply put. We could have applied a partial fraction and calculated a, b, and c. We would have just gone a long way to just end up with the same way. But we could have proved it instead of the final value theorem with our y of t. We would end up with the sum e to the power of negative t, blah, blah. I think it's just a long work that we can avoid thanks to this final value theorem. Okay, well, I can give another example. This time a little bit different, not as easy. I'm gonna give a u in terms of t to be equals to 0, always for t less than 0. And then I'm gonna say t for when t is greater or equal to 0. So now that we have this, we should look up on our lookup tables how to transform from one to the other. So from t to our s. So we can see that it's 1 over s squared. So our capital U of s is equals to 1 over s squared. And I'm gonna say that h is the same thing that I had before, so I'm just gonna copy it and paste it. Yeah, just copy everything. Okay. Now, capital Y of s, that is gonna be equals to what? It's gonna be equals to 1 over s squared times this part here. Okay. All right. So now we can put in our values. Let me write this a little better. So we say that the limit as s approaches 0 of y of s, y of s, sorry, is then going to be equals to limit as s approaches 0 of 1 over s. Well, I can write it out clearly. So these two to simplify, I'm just going to write it simpler. And then we have just this part left. But one thing that you gotta notice now is that the our y of s as a pole, thanks to this part, at 0. And it is at the beginning. A pole at 0 means that we cannot apply our final value theorem. Sorry, yeah, a final value theorem. So no final value theorem. Even though it seems like everything's working out, you can't. And you would see it because when you actually plug it in, you're gonna get a 0 at the denominator and a 4 at the numerator. So you get 4 over 0, which doesn't work. In fact, our actual solution to our steady state, I'm just gonna write a solution without doing all the work, is gonna be equals to t. That means our steady state is unbounded. We don't have a specific value that we want to reach and then solve. I think that's pretty much all you need to know about the steady state input. We can do it a little bit harder, of course, with the cosine and sine. As long as we have our poles all on the left-hand side, then we are fine. Everything works out.